Recording.
Okay. Welcome everyone to this session of the seminar on PDEs and Applied Mathematics. Today we have the honor and pleasure to have with us Professor Rodrigo Lecaros, an associate professor at the Federico Santa Maria Technical University in Chile. He graduated in civil engineering in mathematics and obtained his PhD in engineering sciences, mentioned in mathematical modeling in 2012 from the University of Chile. He has participated and led several research projects, and he has also supervised numerous master's, doctoral, and degree theses. On the other hand, he has developed a great outstanding scientific production in applied mathematics, inverse, and control problems. His main research interest focuses on the area of applied mathematics, with an emphasis on mathematical modeling, inverse problems, optimization, and control. Thank you very much, Rodrigo, for having accepted our invitation to give this talk, and you can start when you want.
Well, thank you, everybody, and thank you the organizer for this nice seminar, and thank you especially Jonah Price for the invitation. Well, let me start. Well, today I will talking about of the coefficient inverse problem for semi-discrete parabolic operator. Well, this is a joint work with Juan Carlos Lopez and Ariel Perez. Juan Carlos is from Colombia and Ariel is from Chile, from the University of Bio in Concepción. Well, this is the skeleton of the presentation. First, I will present the principal goal of the idea of the principal goal, and some result in the continuous case, and preliminaries in the discrete setting, some difficulties, and the strategy and the sketch of the proof of the results. Well, what is the goal in which we are interested in this presentation or in this project? Was to study this discretization of the heat equation. We consider, for example, a heat equation with a simple discretization in the space of the Laplacian with 5 points. And we're thinking in what happens if we consider a potential P, which is some function only depending on the space inside the domain. And that's when we only consider discretization in space, this is a system of ODEs. And of course, we have some right-hand side, and we have a boundary condition, in this case are B0, and we have some initial condition. For this system, the direct problem is given P, we can obtain the solution of these ODE systems, and which is called YP. And the idea is try to looking for or try to understand if it is possible to establish some Lipschitz stability from different P in terms of the solution of the system. The idea is try to obtain some Lipschitz stability in terms of the difference of the solution in some medial time, where theta here is some time in between 0 capital T, and other extra measurement in some subdomain. In our case, this subdomain is a subdomain of our mesh. We here are consider the square mesh in 0, 1. But we know maybe the presence of the numerical approximation maybe introduce some error, which is here is called O of H. And we know, and we want to establish what is the size or what is the dependency of the H of this error. That is the objective of our project. Well, in that sense, in that sense, the typical situation if we have a continuous system in which we know if you have some variables, we can obtain the solution. The inverse problem is the typical situation when we don't have information about, I don't know, the initial condition, the extra force, or in this case, some potential in the equation. But this is in the continuous case, and we can analyze what happened with the system, so on. But the typical situation is when we consider this kind of system, we consider his discretization in some sense. And when we consider this discretization, of course, the inverse problem has some discretization. Well, our work is trying to understand what happened only in the discretization sense with the inverse problem. No use the continuous representation or approximation of the whole system. The result in the continuous case. What is known in the continuous case for this kind of problem? Well, we can find this work by Imanovilu and Yamamoto, where they study this very general system where A represents an elliptic operator, very general elliptic operator. And in this case, they have this result, this term, where he obtained the ellipse stability in terms of the solution in some times and some extra measurement in some interior domain. It is W. Of course, they obtained this expression for the system in the continuous case. Of course, some assumption, for example, they need some extra assumption which has involved alpha. They need the assumption of the solution in the medial time or in the time where they make a measurement. It's positive in the space. It's strictly positive. This is the typical situation for the inverse problems. We need some extra assumption in order to guarantee the possibility to establish the in this case, the stability result. Well, what is the strategy in the continuous case? The strategy is they consider a Kalman estimate where they have some energy of the solution. Here is E. This energy is bounded by the right-hand side and some extra term, which is called observation terms. The next is introduce an extra term from below, which is the solution in the medial time. When the people increase the Kahneman, including this kind of terms, it's possible to following the idea of Bukin and Klimanov for establishes the stability result for the inverse problem. Well, then the key point for the proof or study this kind of problem, it's the Kahneman inequality. This is the structure of the Kahneman inequality where we have here the energy. This energy, it's represent the more high terms in terms of the derivative. Here has the derivative, the solution derivative of t, and the second derivative in space, with some weights. And other energy term which involve terms in which involve terms from less derivative in space. And under you have the right-hand side of the equation, G, and you have the extra term which is called the observation terms. In the works for study this problem, we need the people need two Kahneman estimate for the two potential. In this case, for two Q's equal 0 and 1. The important issues is the weight. We have the weight which depend on the time, and we have the weight which depend on the space. In this case, theta represents the weight which depend on the time. It's singular function. It's singular in 0 and singular in capital T. That is very important for the Kahneman, for obtain the Kahneman, and it's very difficult when we study the numerical, or in this case, the numerical representation of the equation. This function is positive and it goes to infinity in 0 and capital T. And the space function is negative. Then the exponential here appear in the weight of the integral, it's exponential of the negative function. For that reason, when t goes to 0 or goes to capital T, this exponential goes to 0. That is very useful in the continuous case. Well, what happened in the discrete setting? Let me show you, or let me talk about some preliminaries about the discrete setting, where for the discrete setting, we have here n is the dimension in which we are working, and capital N represent the numbers of the node. Then H represents the size of our mesh, and we have our mesh in the square 0, 1 in dimension n. We have a function defined over the mesh, and we are working with a finite differential scheme. For that reason, we consider this mesh, we are called the dual mesh, which represent the medial points. The medial point to the left and the medial point to the right in any direction of the mesh. And of course, we can define the some node in the boundary, which is called the boundary in the direction A. And of course, the whole boundary and the close of the set. Let me show you some picture for understood in better form this representation. Here, the blue points are mesh in the square 0, 1. And of course, we have the direction E1 and E2, where we are moving the mesh. Here appear the medial points, which are the dual mesh. In black, we can see the medial point in the direction E1, and in red, we can see the medial point in the direction E2. These medial points represent the corresponding dual mesh in the direction 1 or in the direction 2. And of course, we can include the boundary term, which is here appear in the boundary. And we have two boundaries, one boundary in the direction E1 and boundary in the direction E2. And of course, the close of the set is simply the interior mesh and the boundary. Why we do that? Because we need to consider the derivative. And the derivative in the discrete setting, the problem with the final difference scheme is where we are defining the derivative. Because we have a point here, and where you are defining the derivative, at the left or at the right or in the point. For that reason, one of the definition we are using is consider the derivative in the medial point. Then the derivative, the operator we are called the derivative, is operator which is evaluated in the dual mesh. Then we are here consider the translation to the right and translation to the left in the direction I of the function. This translation you can see here is 1/2 translation. Therefore, the function u always is evaluated in the original mesh. But in that sense, this is the definition of the derivative, is one of form to consider the derivative defined in the medial points. And of course, a natural definition is consider the average operator, which is again represents some extension to the function u to this extra point in the medial point. Why we consider these definitions? Well, extra definition is consider the boundary terms, and in the boundary term we can consider some expression for the normal direction and the normal derivative, the normal component of the derivative, the normal component, and some extra definition. Well, here is the definition of the normal component. And some extra definition is very interesting because it's the trace operator. The trace operator is no more of the projection of the function u in the boundary, because the u is only defined in the interior medial points, and we need to, in some computation, we need to project this solution to the boundary, and this is the trace. Actually, this is exactly the definition, the trace in the continuous case. We remember when the people define the trace, you consider a flat boundary and you project the interior solution to the boundary. This is exactly the same situation, because we use here our boundary is flat. With this definition, we can consider some definition for the integral. His is no more of the sum of the value or evaluated the function over the mesh multiplied by this factor, which is represent the scalar factor of the volume. And of course, we have obtained some representation for the integral over the boundary. With this definition, it's possible to obtain this expression, which represents the integration by part, or the dualization of the differential operator. We can pass the differential operator from function b to the function u. And when we pass the operator from one to the other function, of course, we pay a price. This price is we change of the mesh, and we have extra term on the boundary. This is the typical situation in 1D. There are several works where people use this definition, but maybe the notation is new. And of course, we have some integration by part for the average operator, but the average operator, the extra term over the boundary, is more or less is an error term. Actually, you can see here explicitly the dependency of the size of the mesh. Well, with this definition, what are the difficulties in the discrete setting for our problem? Well, this example is very famous. It's example, for example, when we consider the discretization, for example, harmonic function, here is the Laplacian of, we are consider the Laplacian of u equals 0, and in the discrete sense. And what happens if we consider u and the normal derivative of the u is 0 in a part of the boundary? Well, the result is u is not 0 in the whole mesh. That is not intuitive, because in the continuous case, that is a classical unique continuation property. If the harmonic function is 0 in a part of the boundary, the function and the normal derivative of the solution is completely 0 in the domain. Here, for example, in 2 dimensions, we can consider this definition of the Laplacian, which is the classical fine point discretization, which is represented only for sum the neighbor, 4 neighbor, and minus 4 times the value of the function in the original point. And with this definition, if, for example, we consider here our mesh, remember the equation of the harmonic, the solution is harmonic, then the equation is only valid in the red point, which are the interior point of the mesh. The blue point represents our boundary condition. Then what happens if we consider a solution which satisfies the Laplacian is equal 0 in the interior point, and we consider the 2 first columns are 0 the solution? That is our representation in the sense in this phase of the square, the u and the normal derivative of u are b0. With this definition, only with this definition, we can extend zeros using the equation inside of the domain, but only in this point. In the rest, we don't have information. Therefore, it's possible to fix the rest of the red point in order to have a solution which are not 0 in this discrete setting. This example is in dimension 2, and in dimension, again in dimension 2, we have this other example, which is very interesting because this example is by Otarek Kavian. And this example shows you we have this function in dimension 2, which is completely 0 outside of the diagonal of the domain. In the diagonal is oscillating function from 1 to -1. And this function, if you compute the discrete Laplacian, minus Laplacian, we have this function, it's a eigenfunction. And his eigenvalues, it's 4 over h squared. Therefore, we can see the eigenvalues doesn't converge to the continuous one. Actually, these eigenvalues go to infinity, has a blow up when h goes to 0. For that reason, there are many authors say the problem when we consider a discretization, you have spurious eigenvalues and eigenfunction which produce anomalous situation in the solution. Actually, with this example, it's possible to prove, in the case of the semi-discrete heat equation, semi-discrete wave equation, or fully discrete heat equation, for all of this equation, if we consider a control region which is doesn't touch the diagonal of the domain, these systems are not controllable. And that is very unintuitive, but this happened. Actually, there are recent work where Manuel Prado proved this can be, it's possible to extend to the stochastic heat equation. Well, there are here some reference for the semi-discrete or fully discrete system. One of the more important authors in this topic is, for example, Framboyer, Le Rousseau, and of course, Victor Santamaria, the previous speaker, has a lot of works in this topic. Well, what happened for a coefficient inverse problem? Because the previous works are related more with control, not with inverse problem. But for our inverse problem, we can consider a very general expression, a discretization of the parabolic system, the parabolic operator. Here, the first part represents the discretization of the Laplacian, the second part of the gradient, and some extra potential. If we consider this system, here we use the notation of the previous definition of the differential, and of course we need to introduce the wave function for the Kahneman. One of the important situations is the wave function, especially in the dependency of time. We need to introduce some perturbation in order to avoid the blow up of this function in 0 and capital T, because some of the tools using for obtain the Kahneman is Taylor expansion. In Taylor expansion, it's not true when the function is not bounded. For that reason, we need to include this extra parameter, which is delta. And it's very important to observe delta. When delta goes to 0, we recover the function in the continuous case. But now we don't have the blow up. The spatial function, it's exactly the same of the continuous one. And well, with this, we obtain this result. This result is under the typical assumption for two potential bounded in L infinity. And of course, if we have two solutions for the problem, we can obtain, and of course, one of the solutions has this bounded from below, we can obtain this Lipschitz stability for our inverse problem. And this Lipschitz stability is the difference also. The difference of the two potential P is bounded for the measure of the measure of our inverse problem. This measure are the difference of the solution in the medial time, and this extra term in some part of the domain, which is this measurement is for all time. But here we observe appear some extra error. Remember when I started the talk, I say we're looking for what is the form of this error. Well, actually, the form of this error is this one, which is the difference of the solutions, but the derivative of t of the solution and t equals 0, but multiplied by this exponential, which has this very nice behavior, because when h goes to 0, this term disappears. How we obtain that? Well, let me show you the idea and the sketch of the proof. First of all, the Kahneman estimate. Boyer and Le Rousseau in 2014, they proved this Kahneman inequality for the semi-discrete system, where here we have the energy terms and the right-hand side. but they appear two errors. Here are in the red terms, an error in 0 and error in capital T. These errors are very bad because on front of this error appears this term, which is the potential of H is -2. Then this is go to infinity when H goes to 0. But the form, Le Rousseau and Boyer using this Kahneman in order to prove the controllability. But in our case, the principal problem is how we control this term. In order to control this term, we observe it's possible to consider theta in 0. Remember, theta in 0 now is not infinity. The behavior of the theta in 0 depends on delta. Then we need to relate the delta with H. In order of delta, control this blow up of H here in front of the integral. Well, with this, we try to improve the previous Kahneman, including this extra term in the medial time, and what's possible to do. And of course, here we have the right-hand side, and we here define the operator of the right-hand side, which include the potential P. And of course, we have a lot of weight, rho B, rho A, and rho C, where these weights are defining here. In that sense, one of the important observations at the right-hand side, where we have rho C here has this blow-up term, which are our idea is controlled with theta 0, but they have two other extra terms. That two other extra terms, it's because this Kahneman inequality doesn't consider the term in capital T. We don't have the error in the capital T of the previous Kahneman here appear. We only have the error in T equals 0. And of course, we have other error terms, very bad terms, in the principal terms in the Kahneman. Well, the other improve of the previous Kahneman, if we can consider here the term with the more high level of the derivative. In that sense, the discrete derivative and the time derivative. With this Kahneman, in order to prove this Kahneman, we need to prove these two lemmas. The first lemma was including the term in the medial time. This term bounded from A of y and J of y, which are the energy, the left side of the energy from the Kahneman, here appear here, and one extra term, which is the term of the solution. Okay, that is not bad because remember the original Kahneman has this term in the discrete setting. In the continuous case, this term doesn't appear because theta in 0 is plus infinity and phi is negative. Therefore, this term is 0 in the continuous case. And the other lemma, important lemma, is obtain a bounded from the solution in capital T in terms of the solution in 0. This estimate is very simple because our system it's the classical heat equation, therefore is dissipate. Actually, this is the dissipation of the system. And in the discrete setting, it's possible to prove exactly this dissipation. Using the Booking-Klibanov method, we can define, using the Booking-Klibanov method, we can define, in that case, the set, which is the difference of both solutions, and U is the derivative of set, and we're looking for what equation satisfies U. The equation is exactly the same operator of the original one, but with the weight P2. This is the equation, and the right-hand side here emerge the difference of P2 and P1. And of course, in the medial time, we can estimate again P2 minus P1. Of course, bounded from multiplied by this term. which we are assuming is different to 0. For that reason, using Kahneman inequality for the function u, we can estimate u in the medial time, in t/2, in terms of the right-hand side of the equation and the solution in interior domain and the solution in t equals 0. And the right-hand side is given in terms of the difference of p2 minus p1. And with this, combining this previous equation, we obtain this expression, which is the classical situation for this kind of estimate. And here appear the difference of p2 minus p1, and here appear exactly the same. The idea of this expression is using a triangular inequality and estimate, and this term, with this term in the left, try to absorb this term to the right. The idea of the weight, in this case, row A, is less than the weight appear in this part. The problem is the integral in the left side, it's only in space because all the terms are evaluated in time. But the terms in the part of the right-hand side depend on time. This integral is in time and in space. For that reason, we need this lemma. With the lemma, it is in order to estimate the integral, the whole integral in time and space, only in terms of the medial time. And this is possible. Of course, we pay some price here, but this price is less than 1 for the potential here appear p. For that reason, it's possible to control. Observe in this case, the potential appear in row A, it's 0, doesn't appear this term. For that reason, when we use the estimate, we has appeared 1 over the root square of S, the parameter S, which is the parameter of Kahneman. With this technique, we can finish, and this is the classical situation in order to prove our principal result, which is this stability. Our second objective was try to produce an algorithm in order to recover P. The algorithm for recover P is this. This is our algorithm, which this is the proportion of the algorithm. This algorithm has several steps, but let me show you what are the important steps in order to recover the potential. We start with some unknown P, for example, P0 equals 0. And the idea is, in the step 1, compute the solution associated with the pk. Well, we compute the solution, and then we set mu k and nu k. Mu k and nu k represent the gaps or the error respect to our measurement, because we know these terms in this subdomain, and we know this term in the initial time. Therefore, this mu k and nu k represent the error for our answer, which is pk. And with this error, now we consider a new approximation, is mu star. U star is the solution of the minimization of this functional. This functional is given by this one, which is the right-hand side of the Kahneman inequality. The right-hand side, you can see here the right-hand side, but here it has the error in the measurement part, because we consider here mu and nu, which in any steps represent the error, and it's possible to prove this functional is convex. It's well, has all the quadratic property in order to guarantee the existence of the minimums, and then we can compute this minimization. If we have this minimum, with this minimum, it's possible to compute a new approximation for P given by this expression. In this expression, it's very important. Y0 is actually the unknown solution, but the solution in the medial time, where we are measuring that and we assuming that is different to 0. For that reason, pk is possible to compute in this form. And if you compute pk in this form, the final step is project this pk in order to guarantee a sum bounded, which is necessary for the convergence of the algorithm. Well, this strategy is, I don't know, it's classic or not, but it's very common in the case for the in the problem where the people using Booking-Klimanov method using Karleman inequality. That actually that was introduced by Lucie Boudouin, Maya Boudin, and Sylvain Hervedosa. They introduced that, but for the wave equation. We adapted that in the case of semi-discrete and in the case of the semi-discrete and parabolic equation. With that, we obtain this theorem. This theorem say, well, under the classical assumption for the stability of our inverse problem, we can prove our pk satisfies this inequality, which is in some sense, if we observe, of course, these are some sense that are norm, but with some weight. Of course, this weight has a relative with the Karleman inequality. But the important part is this term which appear on front of the estimate. Then we need to take S, the parameter of Karleman, large no, in order to guarantee this term be less than 1. Because in this case, the sequence pk well, it has a contraction principle here, but with these norms. And then that proves our algorithm converges to the unknown function p star. The problem of this numerical or algorithm is the implementation. What is the problem for this implementation? The problem for this implementation is the weight using here are very large, because here appears parameter S, but remember phi is exponentially of the other parameter which has lambda. And when we estimate the Karleman, we assume large, the lambda is large enough, then we have exponentially of the exponentially for huge term. For that reason, it's very difficult to compute this expression and very difficult to implement the algorithm. For reference about this algorithm, maybe, I don't know, sure, but the people call this algorithm reconstruction using Karleman inequality. For a very nice reference, we have here this paper by Lucie, Maya, and Sylvain, where they present this algorithm, but in the case of the wave equation. They develop a lot of, they develop several works in order for the wave equation using this algorithm. Here you can see for the wave equation. Actually, they improve the presentation for a new Karleman using less parameter in order to compute the solution. Finally, we have this nice work by Murier, Maya, and Erika for the 2021, where they developed this algorithm in the case of the heat equation, but in the continuous case. Well, summary of my presentation, we studied the case in Rn. For the semi-discrete problem, we obtained an equivalent version of the unit continuation plus some error terms, and we improved the Karleman inequality for the semi-discrete parabolic problem, and it was possible to control the part of the error term emerging by the Karleman inequality, and we propose a convergent construction algorithm to recover the potential P. What is necessary to continue study? Well, the numerical implementation of the algorithm, and to study the full discrete problem or the discrete in the space and time. Well, that is my presentation. Muchas gracias.
Okay, thank you. Gracias, Rodrigo, for your great presentation. And now we will give the opportunity to the audience if they want to ask or comment something. I think that Juan uses to open the micro to the audience just in case they want to ask something. Is there any question or comment? Meanwhile,
One question, maybe?
yes, please go ahead.
Last
Yes.
question. For controllability, this algorithm also has the same problem of implementation, null controllability.
Well, for null controllability, the problems are very similar. Of course, in this case, the people use the backward equation. We use the forward equation, but the problems are very similar. Actually, they use delta again of us in order to control the error which emerged in the observability inequality. This technique was developed by Boyer and Le Rousseau. But actually, they can prove controllability. Actually, the controllability it's not true in general for the semi-discrete case. But they prove some, it's called phi controllability, which is other notion of the controllability, which include some extra term which go to zero when the size of match go to zero. That's a new notion of the control. It's not exactly of the approximation controllability, and it's other notion, and that was using in the control for the heat equation to zero.
Yes. Yes. More questions? I would like to say also that I have seen that there is deep work behind these results and also many technical details, no, in the Karleman estimates, and yes, it can be appreciated. And I was curious because in some Karleman inequality that you call, I think, a new Karleman inequality, where the weights rho A, rho B, and rho C were appearing here. I was curious because how do you know that you needed those type of weights? Because they are not simple, no? And
Oh, yes,
how
but
did you build that? Yes.
no, well, we spend a lot of time trying to express that in the short form,
Yeah.
but at the end are very, I don't know, intuitive, but in some sense, because here is the typical weight because for example, rho A is the weight in the right-hand side of the equation, and this is the typical weight, but
Yes.
including this extra term. This extra term appeared simply because in our case, because this is the expression for the Boyer, but here have the term in capital T, and we to drop the term in capital T. In order to estimate the term in capital T, we consider this lemma 2. Then the energy or the nominal 2 is estimated in terms of the solution in T equals 0. For that reason, the solution of the Boyer, the Kalman of the Boyer, has these two terms for the solution multiplied by the solution capital T. When we use our lemma, we translated this weight to the solution in T equals 0 and the solution of the right-hand side of the function. For that reason, emerging the weight emerging in this form. It's very funny because when we investigated the algorithm for the convergence, we observe it because the functional we need to minimize, it's exactly the right-hand side of the Karleman inequality. This is our algorithm, which is this one. But actually, it's not necessarily this functional. We can consider any functional which bounded this functional from the right side. Therefore, if you approximate the weight for something more high, you can again obtain a better estimate of the function you start.
Yes, it was surprising for me because sometimes it's not easy to find the appropriate Kalman weight. So there was a very big and yes, it was interesting. And also another question, I don't know if I have understood well, but the observation domains that you have considered in the inverse problems are in the interior, no, of the domain. Yes, no? Okay.
Yes, it's an interior domain. This inverse problem always was studied with the measurement in the boundary. But we don't have this, we don't know how to do that because we don't have the Kalman with boundary measurement. And in this sense, it's necessary to develop the Kalman with the boundary measurement, boundary estimate, in order to try to estimate again everything here in this work. Because the original Kalman in which we started was the Kalman used by Boyer and Le Rousseau, and Boyer and Le Rousseau is the interior domain.
Yes. Yes, thank you, Rodrigo. Is there any question? If not, we will thank again Rodrigo. Muchas gracias, Rodrigo. And we will stop here. And I would like